Okay, let's try a thought experiment. Imagine really, truly empty space.
Uh,
Not just, the best vacuum we can make here on Earth, but way out there. Far from stars, planets, even stray atoms. Just nothing.
Pure void.
If
It's,
you are there, what happens?
well, if you asked a physicist from, say, 100 years ago,
Mm.
using classical physics,
Yeah.
they'd say absolutely nothing.
Yeah.
Just stillness. No light, no energy, no action at all.
Which kind of makes intuitive sense, right? If there's nothing there, how can anything happen?
Exactly. But as we keep finding out, the universe, at its very roots, it doesn't really care about our intuition.
Hey, yeah, it tells us that again and again.
Right. So quantum field theory, it paints a very different picture. That perfect vacuum isn't empty. Not at all.
It's active.
You could say that. It's
Yeah.
described as a dynamic, sort of seething realm. It's humming with potential energy.
Wow. So instead of just blankness, quantum mechanics says this empty space is actually full of, what did you call them? Virtual particles.
That's right. Fleeting things, constantly popping into existence, then vanishing almost immediately. Like tiny flickers in reality itself.
Okay, that's already pretty mind-bending.
And it leads to an even weirder prediction. Could you actually get something real, like light, out of this apparent nothingness?
Conjure light from the void. That sounds wild.
It does. But it's a genuine prediction, something scientists have been wrestling with, trying to figure out how to maybe even observe it.
And that's where we're headed today. This is our deep dive into some really fascinating new work, a powerful simulation.
Yeah, by researchers at Oxford and also the Institute of Superior Technico in Lisbon, they've managed to model this really bizarre prediction in, well, incredible detail.
Giving us a glimpse of what happens when you push that empty vacuum really, really hard.
Exactly. And our discussion is based on some great reporting, particularly an article from ZME Science,
Mhm.
that really laid out why this simulation is such a step forward.
So welcome everyone to the deep dive. This is where we take complex stuff from sources like that ZME science piece and really unpack it. We hope you enjoy this exploration of the quantum vacuum.
And if you do, feel free to engage with us in your input, your questions, maybe even ideas for future topics. It all helps us figure out what to dive into next.
Okay, let's really get into this. The quantum vacuum isn't empty. Why is that so counterintuitive for us?
Well, our everyday experience is all macroscopic, isn't it? Big things. Empty space just means nothing's there.
Right. An empty box is empty.
But quantum field theory works differently. It sees fundamental particles not as little points, but as excitations, ripples maybe, in underlying fields that fill all of space and time.
Like the electromagnetic field, for example.
Exactly. And even when a field looks empty, no real particles, like photons that we can see, quantum mechanics, says there are still these constant, unavoidable jiggles, fluctuations in its energy.
Ah, and those are the virtual particles?
That's the idea. Think of them as temporary pairs, like an electron and its antiparticle, a positron. They borrow energy from the vacuum to exist for a tiny fraction of a second.
And then annihilate each other, paying the energy back.
Precisely. It's all governed by the Heisenberg uncertainty principle. You can have these little energy fluctuations, these particle pairs, as long as they happen incredibly fast.
Like tiny energy loans the universe makes to itself, due back almost instantly.
That's a pretty good analogy, yeah. And normally they pop in and out so fast with so little energy we just can't see them directly. They're part of the background hum, the vacuum's zero-point energy.
Okay, usually unobservable. But the source article and the simulation, they're about making them matter somehow.
Yes, exactly. That's where the extreme conditions come in. You need something incredibly powerful, like an ultra-intense laser beam. That super strong electromagnetic field can sort of store up the vacuum. It interacts with it, pours energy into it, and can affect those virtual particles. It can make them, let's say, more real for a moment, or change the vacuum's properties in ways we can measure.
And that altered vacuum, that's what leads to light interacting with itself, which sounds impossible.
Totally impossible in classical physics. You cross
Yeah.
two flashlight beams, they go right through each other. Photons just don't interact in a normal vacuum.
Like ghosts passing through each other.
Yeah. But add that super intense laser field, the vacuum isn't normal anymore. It's temporarily fizzing with these energized virtual particles, and they can act like a medium.
Ah, so the photons don't hit each other directly.
No, but they interact with this altered vacuum state, and through that, they can influence each other. They can scatter, change direction, or even create new photons.
Okay, the intense field changes the vacuum, and the changed vacuum lets light interact.
Got it. What specific process did this simulation model? They focused on something called vacuum four-wave mixing. It's a specific prediction. Imagine you take 3 incredibly intense laser beams
3. Okay.
and you make them intersect in this vacuum. Their combined field is just enormous. It doesn't just tweak the vacuum, it can actually promote some of those virtual particle fluctuations into becoming real, observable photons.
Wait, 3 laser beams go in, and a 4th beam comes out of nowhere.
Seemingly out of nowhere, it emerges from the vacuum itself. The 3 beams disturb the vacuum just so, and the vacuum responds by radiating new light, leveraging those background fluctuations amplified by the intense fields.
The article called it akin to summoning a spark from thin air.
That's a great way to put it. You're coaxing light from the void using extreme energy.
Incredible. And they also look at something else, vacuum birefringence.
Yes, vacuum birefringence. Another predicted quantum effect in strong fields. Normally, vacuum is isotropic, same in all directions. Light just goes through, its polarization doesn't change. But put in a super strong magnetic or electric field. The vacuum itself effectively becomes directional, anisotropic.
Like shining light through certain crystals. They can rotate the polarization.
A bit like that, yeah. But here, the crystal is the vacuum itself, temporarily modified by the intense field. So light passing through might have its polarization state changed, depending on the field. Again, requires immense fields.
Which brings us to the simulation, this Oxford and Lisbon collaboration, using the OSIRIS framework. What did it actually let them see?
Well, until now, these ideas were mostly calculations on paper, or incredibly difficult to even attempt to measure. This simulation, it gave them what they called an unprecedented real-time three-dimensional window into it all.
So not just abstract equations, but a dynamic picture.
Exactly. A sophisticated computer model showing, step by step, how these intense lasers would actually interact with the quantum vacuum, change it, and produce these effects, like running the experiment virtually.
And it captured the details, the quantum signatures.
Yeah. Yes, the full range. Meaning, if light is created or altered, what are its exact properties? Its angle, its energy, its polarization?
Yeah.
All the specific fingerprints that would tell an experimenter, yes, this is the quantum effect we're looking for.
And crucially, this wasn't just theory for theory's sake. It seems really practical for the people running the actual experiments.
Oh, absolutely vital. Building and running these super lasers is massively complex, incredibly expensive. You don't want to be guessing where to look.
Right.
The simulation showed how real-world issues, things like the beams not being perfectly aligned, or maybe focusing slightly differently, how those could actually affect the results you get.
It's like giving them a troubleshooting guide before they even start.
Pretty much. A crucial dress rehearsal. They use realistic models for the laser beams themselves. Gaussian beams, that's how these powerful lasers actually behave. And they tracked everything in both space and time.
Why is time important there?
Because it tells you when the interaction is strongest, when the new light might appear, and for how long, and where it appears spatially. That combination is gold if you're trying to set up detectors to catch a faint signal.
They even saw specific predicted distortions, didn't they? Like astigmatism if the beams cross at an angle.
Yes. And those kinds of specific detailed predictions are exactly what you need. If the experimenters see that particular kind of distortion, it massively boosts their confidence that they're seeing the real quantum vacuum effect, not just some experimental artifact.
So, okay, why is this simulation such a big deal right now? What's the context?
It's really about convergence. The theory has been around, the simulation tools are getting incredibly powerful, and, well, the hardware is finally catching up.
Meaning
This new generation of laser facilities the article mentions, they're coming online or just started operating around the world, places designed to reach exactly these kinds of extreme intensities.
Can you give some examples?
Sure. There's the UK's Vulcan 2020 facility, which has been upgraded. There's the pan-European ELI extreme light infrastructure, especially the site in Romania. And China's launching the incredibly powerful 100 petawatt shine laser.
100 petawatts. That sounds astronomical.
It is. These are machines built precisely to probe these fundamental regimes of physics, including the quantum vacuum.
So the simulation is basically the user manual for these new machines for this specific kind of experiment.
It provides critical guidance, absolutely. Professor Norris from Oxford put it nicely. He said this is a major step toward experimental confirmation of things that have been, well, mostly theoretical until now.
It tells them where and when to point their detector.
Exactly. It tells them precisely when and where to look for that faint spark from the vacuum or that subtle twist in polarization. Without this kind of detailed simulation, searching for these effects would be, Well, like finding a needle in a haystack doesn't quite cover it. A needle in a universe-sized haystack, maybe?
It bridges the gap between blackboard equations and something potentially observable in a lab.
That's the key step.
Hmm.
But it's not just about confirming things we already predicted. The potential actually goes further.
Oh.
Yeah, the simulation framework itself, the OSIRIS code they used and refined, it's very flexible. The source notes that these simulations open doors to discovering new physics.
New physics, like what?
Well, they can adapt the simulation to look for the signatures of hypothetical particles,
Mm-hmm.
things beyond the standard model.
You mean things like dark matter candidates?
Potentially, yes.
Yeah.
Things like axions or maybe millicharged particles.
Mm.
These are particles we suspect might be out there, making up dark matter. But they interact very, very weakly with normal stuff, including light.
So how would the simulation help find them?
The idea is maybe under these extreme conditions in the vacuum, pumped by these intense lasers, these exotic particles might leave a tiny subtle fingerprint.
How?
Perhaps they'd alter the way the vacuum responds just slightly differently than predicted by standard quantum electrodynamics alone. So you run the experiment, guided by the simulation for the standard effect. But maybe the light comes out at a slightly different angle. Or the polarization change is a tiny bit off from the simulation's prediction, that tiny discrepancy. That could be the hint of new physics, maybe the signature of axions or something similar interacting.
Wow. So it's both a confirmation tool and potentially a discovery tool for the unknown.
Exactly. It's a powerful new computational method. Professor Silva from Lisbon said it'll greatly assist a whole range of experiments being planned at these new facilities. It's pushing boundaries on all fronts: simulation, experiment, fundamental theory, all focus on what we thought was just empty space.
Okay, let's try and boil this down. What are the key takeaways from this deep dive?
All right, first, maybe most fundamental, the quantum vacuum. It's not empty. It's alive with fleeting virtual particles and potential energy.
Second, physics predicts that if you hit this vacuum with incredibly intense lasers, you can actually make light interact with itself or even generate new light straight from the vacuum, like in vacuum four-wave mixing.
Third, this new simulation from Oxford and Lisbon gives us the most detailed, practical picture yet of exactly how this might happen, showing the signatures and accounting for real-world experimental factors. It's a vital guide.
And finally, this work is perfectly timed for the new generation of ultra-powerful lasers coming online. It moves these weird quantum ideas closer to actual experimental tests, and the same tools might even help us hunt for new exotic particles like dark matter candidates.
Yeah, it's really about taking these almost sci-fi concepts and making them part of experimental science, giving us a concrete path to try and see them.
It really does circle back to that initial thought, doesn't it? The idea of light being conjured from nothing just fundamentally challenges how we think about space.
It does.
It makes you wonder, if that's happening in the vacuum, what else might be lurking there, just waiting for us to find a clever enough way or a powerful enough tool to reveal it.
The universe still holds plenty of secrets, especially in the places we assume are simplest.
Definitely gives you something to think about next time you look up at the night sky. Keep learning, keep questioning, and stay tuned for our next deep dive.